Thanks very much for the invitation to speak here. It's good to see a lot of friends in tiny windows on my computer. And yeah, so let's get started. I've got a little bit of an unusual setup here. So can you see the slides? Okay. So I'm going to use two Keynote for the first part of the talk and Beamer for the second part of the talk, and that's not some kind of intellectual decision that I made. It's just that I'm combining two different talks that I've given in an unusual way for this particular audience, and I'm too lazy to change the formatting. So all of it, though, is joint work with Oliver Lorscheid, but this represents a couple of different papers. So part one, will be a bit more elementary, and we'll be talking about polynomials in one variable over some exotic algebraic structures. And then part two will be more about matroid theory and how the same algebraic structures illuminate some considerations about matroids. And there's some link between these two parts of the talk, but you can think of it as two separate talks with a unifying general theme of what I call pastures. All right, so let's get started. And I spilled something on my keyboard recently, which is making it hard to change slides, but I'll do my best. So our story begins with René Descartes, who discovered something rather interesting that I always found something of a curiosity. Now I feel like I actually, to some extent, understand it. And this is called Descartes' Rule of Signs. So to remind you what this says, you have a polynomial p of x, coefficients little a sub I that are real numbers. And Descartes' rule says that the number of positive real roots of this polynomial is at most the number of sign changes in the sequence of coefficients. Okay, and so of course you can also count the number of negative real roots if you replace x by minus x, and so now you're looking at the coefficients with alternating minus signs in front of them. And yeah, so the key feature of this that I'd like to emphasize is that we get an upper bound for the number of positive or negative real roots, which depends only on the signs of the coefficients, right? So we're saying something about signs of roots in terms of signs of coefficients. Now, okay. So there's kind of a supplementary fact, which I think maybe was not actually formulated by Descartes himself. I forget the history now, but anyway, the difference between the number of positive roots and the number of sign changes is actually always an even number. So it's an upper bound, but there's also a parity constraint. So this is something special about kind of the real numbers, the fact that Galois group of C over R has size 2, and I suppose one could work that into the theory I'll be describing, but I'm not going to do that here. So just as a quick example, here's a quartic polynomial, and you can see that there are, for f of x, you have two sign changes given by those blue curly arrows. So there are at most two positive real roots. And there are also two sign changes for f of minus x. So there are at most two negative real roots. And in fact, if you look at the graph of the polynomial, you'll see there are actually no positive real roots, and there are indeed two negative real roots. So in this case, one of these bounds is sharp and the other one is not. Okay, so that's as much as I'll say right now about Descartes' rule. The second hero of our story is Isaac Newton. And he discovered something that's maybe more familiar to the tropical audience. So to say it in modern language, let's just remind ourselves what evaluation is. If K is a field, evaluation is a map to R union infinity with the property that only 0 has valuation 0. Oh, I guess this should have been, I think I'm mixing additive and multiplicative notation. Sorry, this should have said valuation is infinity if and only if X is 0. Valuation of X times Y is valuation of X plus valuation of Y, and valuation of X plus Y is greater than or equal to the minimum. Okay, so, but you all know this because you're tropical geometers. So examples of valuations could be order of vanishing of a Laurent series at a t equals whatever, like 0, or the p-adic valuation on the rationals. And the key thing that Newton introduced was the Newton polygon. So if you have a polynomial with coefficients in some valued field K, then you can plot I comma valuation of A sub I. And once you plot those points, you can take their lower convex hull as shown in the diagram here. And then from that lower convex hull, you can read off certain invariants. In this case, the key things are, if you look at the boundary of that lower convex hull, we have a finite union of line segments. And the slopes of those segments here are -2, -1, and +1. And the multiplicity is the length of the projection to the x-axis, or the horizontal length of the segment, and those in this case are 1, 3, and 1. And the point is that from this information, we have Newton's polygon rule, which says that the number of roots with valuation equal to s is at most the multiplicity of the slope minus s in the Newton polygon. And so again, the key fact is that the flavor is similar to Descartes' rule. We can give an upper bound for how many roots have a given feature in terms of the coefficients. And in this case, we're bounding how many roots have a given valuation in terms of just the valuations of the coefficients. And before, we were looking at number of roots with a given sign in terms of the signs of the coefficients. So these do indeed have a similar flavor to them. And I'd like to discuss how to unify these two rules. Okay, so this was just, in that case, illustrating what this all means. Okay, but I think you understand that. So in order to unify them, we will look at the work of Mark Krasner. Probably, if I had shown you these three pictures, most people would know Descartes and Newton, but not Krasner. But Krasner did some very interesting things. And one of the things he did was to introduce the notion of a hyperfield. So I'll be more precise later in the talk, but roughly speaking, this is a structure that's just like a field, but addition is allowed to be multivalued. Now, actually, the context in which Krasner introduced hyperfields is quite interesting, especially to a number theorist and arithmetic geometer like myself, because Krasner was essentially inventing the theory that's now become known as perfectoid geometry back in the 1950s. And so people like Fontaine and Schulze have given much credit to this pioneering work of Krasner. And it was the very same paper in which he introduced hyperfields. Anyway, I won't talk about that aspect of things, but hyperfields have, for example, a multiplicative identity element called 1, or in this particular font, it looks like an I. Sorry about that. An additive identity element 0 and a negation map, x goes to -x. So that's all good. So what are they, what's the difference? Well, the addition, as I said, is multivalued now. And so the hypersum of x and -x, we can't set equal to 0, or we could, but that would be dumb. We just require that 0 belongs to the set x plus -x. Okay, so that's what the involution of negation that's the property it should have, is that 0 is always in the hypersum x plus minus x. And in fact, there should be a unique element minus x with that property. Okay, so maybe I'll skip the editorializing sermons about multivalued operations. So there's a funny quote by Vero that, I don't know, you can find on my blog and other places, but I'll skip that here. Because later you'll see that actually you can rephrase a lot of this without talking about multivalued operations at all. But right now, I think that's the simpler way to introduce it. So the Krasner hyperfield, as Kahn and Consani have christened it, is the hyperfield with two elements, 0 and 1. Multiplication is what you think. And hyperaddition is almost the usual thing, except that 1 plus 1 is the set consisting of both 0 and 1. And if that looks strange to you, then you're biased against multivalued. No, if that looks strange to you, just think of 0 as a symbol that really means 0, but 1 is a symbol that means non-zero. And now this all makes perfect sense, because if you add something that's 0 to something that's non-zero, it's definitely non-zero. But if you add two non-zero things together, you might get 0, you might get non-zero. Okay, and that's all that Krasner hyperfield is doing. And so there's something similar where we keep track of not just 0 or non-zero, but also of signs of real numbers. So we represent this by 0, 1, and minus 1. Multiplication is the usual thing because signs multiply exactly like you think, but addition of signed real numbers is a bit unpredictable, right? If you add a positive to a negative, there's no telling what you will get. And that's what this hyperaddition reflects. So it's completely intuitive and simple once you think about it. So of course there are some axioms for hyperfields that I'm not exactly giving because it's boring, and I'm trying to give you the main idea right now. Later will be a little more precise and more general at the same time. So for this purposes of this talk, probably the primary motivation is the tropical hyperfield. And this captures the arithmetic of valuations. So tropical hyperfield, as I said, is real numbers together with plus infinity. And then the multiplication is just the usual addition. Hyperaddition depends on what A and B are. So if A and B are different, then their hypersum is just a single element and it's the minimum. But if A and B are equal, their hypersum consists of all real numbers greater than or equal to either one of them. So this is a little bit of a different point of view than the max plus semi-ring, or in this case, min plus semi-ring. And in my view, which has admittedly become somewhat biased, this is just a much better way of looking at tropical geometry than through the lens of semi-rings, because this really captures the arithmetic of valuations in a much more precise way. And now looking at the zero locus of a tropical zero locus of a polynomial as, you know, the places where the minimum is achieved at least twice becomes a completely natural operation to say that 0 belongs to a certain hypersum. Whereas in the semi-ring language, it's a bit ad hoc. So I'm very fond of this point of view, but to convince you of that, I'd like to give you this unification of Descartes and Newton. And to do that, we have to talk about homomorphisms. But this is basically obvious what you should do. So if you have a map between two hyperfields, it's a homomorphism. If it's a multiplicative homomorphism, and then there's a suitable containment of hypersums. And maybe you have to think a little bit about which direction the containment should go, or whether it should be equality. But I mean, this turns out to be the useful notion of what I've written here. And to justify that, you know, take a look at the following examples. For any hyperfield F, you have a map to the Krasner hyperfield taking 0 to 0 and everything non-zero to 1. And that is a homomorphism with this definition. The sign map from real numbers to S is a homomorphism, which means we're just forgetting everything except the sign of a real number. And if you have a field with a valuation on it, the valuation itself is naturally a homomorphism to the tropical hyperfield. And in fact, a homomorphism to the tropical hyperfield is nothing other than a valuation. So valuations become homomorphisms in this language, which is also nice. So in Oliver Lorscheid's theory that I'll mention later, you can do things like take base change along valuations, fiber products, and categorical things that you would like to do because valuations are just morphisms in a certain category. So this is pretty cool. And it captures what I like to call the algebra of forgetfulness, which is really, to me, what tropical geometry is about. It's a particular case of forgetting certain structure and seeing if what you can still remember is interesting or not. And if you forget too much, it's no longer particularly interesting. If you don't forget enough, then you haven't done anything new. And if you forget just the right amount, then all kinds of new mathematics emerges with new features that we all love to study. But my point is that tropical geometry is, in some settings, much more general than we tend to give it credit for, because we're often talking about just this particular forgetful map given by evaluation. But in fact, there are many other interesting examples. And so to tie this together, suppose you have a hyperfield F. We want to look at polynomials over F. And for now, we'll just treat them as formal expressions like this, where the AIs live in F. Now, what kind of algebraic structure the set of polynomials itself forms is a slightly delicate question that I will not talk about now, but maybe I will later. This is where other technical foundations are better than looking at hyperfields. But for now, I think there's no problem treating these as formal expressions. And what is a root? I sort of told you this already. Alpha is a root of P of X if 0 belongs to the hypersum that I've written down, where you replace X by alpha. And in case it's not completely obvious already, one of the axioms for a hyperfield is that this hypersum operation should be associative in a certain obvious sense. So this makes sense to look at a multifold hypersum. So when F is the sign hyperfield, 1 will be a root of some polynomial if and only if you have at least one coefficient that's equal to 1 and some other coefficient that's minus 1. Right? That's the only way you can get two things to add up to 0 is if at least one of them is positive and at least one of them is negative. And similarly, to be over the tropical hyperfield to be a root, the minimum of AI s to the I should be achieved at least twice. And I guess the first thing that we discovered that seems to be new, although probably in some contexts this was already known, but in this generality, I think we were the first to notice this. There's a natural division theorem here. So you can say whether a monomial x minus alpha divides P of X in the following way. There should exist a polynomial Q of degree 1 less, so that P belongs to X minus alpha times Q. What does X minus alpha times Q mean? Well, it just kind of, it's a set of polynomials, right? So if you would expand out X minus alpha times Q of X term-wise, you would get that the coefficients now have certain hypersums in them. And I just want P of X to belong coefficient-wise to that set. So very concretely, I'm just saying, if you multiply it out, that AI belongs to minus alpha BI, hypersum BI minus 1 for all I. So that's what it means to divide. And now the theorem, it's really a lemma, is that alpha is a root of P of X if and only if X minus alpha divides P of X. And you might say, that must be completely trivial. And it's not hard to prove, but I mean, you do actually need all the axioms for hyperfields to prove this, which I haven't quite given them all to you yet. And it's kind of not as obvious because the remainder is not uniquely determined anymore. Okay, so you can say things like this, but I mean, you don't really have a division algorithm in the usual sense without further discussion. So there are some subtleties here. But nevertheless, this thing you want to be true is true.
And Matt, I have a quick question. If your field, your hyperfield is a tropical hyperfield, what's your subtraction?
So in this case, x minus alpha is the same as x plus alpha. So -1, right? Negative x is just x in the tropical case.
Okay.
Right. So yeah, occasionally we have to be careful with minus signs because you know, there is an involution on the real numbers that's different from the involution I have in mind. So thanks for clarifying that. Okay. This allows us to define multiplicities of roots. And again, I think this is a new definition in the literature. So if alpha is not a root, then its multiplicity is 0. And otherwise, its multiplicity is defined recursively as 1 plus the maximum over all q's for which p is in x minus alpha times q. Right, so it's of course, this coincides with the usual definition over a field, but there's a couple different definitions a priori you could take in this multi-valued situation, and this is the one that actually works. But of course, we didn't know that going in, so I mean, this was the interesting part of the project, was to find a good definition of multiplicity and then try to prove a theorem about it. So here's the theorem, together with Oliver Lorscheid, that you have a homomorphism, for simplicity, let's say from a field K to a hyperfield F, and P is a polynomial with coefficients in K, then you get a certain semi-continuity result or a certain inequality that for every beta in the hyperfield F, the multiplicity of beta as a root of the push forward polynomial is at least the sum of the multiplicities of all the preimages of beta. Okay. This is also very easy to prove, but nice to write down in this form. And the point is, when you specialize this, yeah, question?
There's a question in chat. So you was asking whether this definition of multiplicity is equivalent to the highest power of x minus a dividing p.
No, not exactly. We have some counterexamples in our paper too. I mean, it depends how you ask the question, but no, you can't really phrase it in terms of division by, so like multiplicity 2 is not the same as being divisible by x minus a squared, actually. Because you could be divisible by x minus a squared. Well, okay, I mean, I guess I don't want to get into the exact subtleties here, but we discussed this in our paper. And so you do have to be a little careful. So I'm trying to see if I can see the chat without blocking my own view. Okay, yes, I can. All right, so maybe in the future, I'll be able to see the chat myself. So anyway, multiplicities over the sign hyperfield. So if you look at the multiplicity of 1, which remember stands for positive roots, as a root of p, yeah, we defined it in this recursive way. But in fact, you can show by induction that it's equal to the number of sign changes in the coefficients of p of x. And so together with that general multiplicity inequality that I just stated, this gives you Descartes' rule of signs. So it really is this just general kind of semi-continuity result applied to the hyperfield of signs. And so that's pretty neat, I think. And over the tropical hyperfield, with a little more work, you can show that the multiplicity of a real number s in this recursive multi-valued algebraic sense is exactly the multiplicity of minus s in the Newton polygon. So again, that's an inductive argument using some well-known facts about tropical algebra. And whoops, so together again with the multiplicity inequality, this gives you the theory of Newton polygons. And we also have some things in our paper about when equality is obtained, some sufficient conditions to get a sharp inequality and that kind of thing. So I'll skip that as well here. So this is the promised unification of these two classical facts. And I'll highlight an ongoing project that one of my students, Trevor Gunn, has been working on, which is to generalize this to the case of multivariate polynomials. So I'll just state it as an open problem for now. You can, of course, you can generalize the notion of roots without much problem to multivariate polynomials over a hyperfield. But multiplicities, it's less obvious how to do it, right? So I gave you this inductive description that works well in one variable. It's a little less obvious what to do in several variables. We have some ideas, but I mean, one has to prove everything works as expected, and it's a bit of a challenging problem. But you could imagine n polynomials in n variables that are either sufficiently generic or transverse or something like that. You would, of course, have to define that in this context. And then you could ask if there's similar inequalities and combinatorial descriptions of multiplicities. And one reason you might want to ask this is that a multivariate Descartes rule of signs is still an open problem in general. There's actually been recent work in that direction, but I would say it's still an open problem. And I think this is a very promising approach because we do, in the tropical case, have a pretty good understanding of these multivariate multiplicities, right, coming from tropical intersection theory. And so the goal would be to kind of generalize tropical intersection theory in this more general algebraic framework in a way that would also apply to things like Descartes' rule of signs. And this is something I've been interested in for a while, but you know, we haven't nailed it down yet. So any questions before I move on to part 2 of the talk?
So if you have a finely generated algebra over some non-Archimedean field, can you just look at the like the tropical number value points in the hyperfields, and is it the Berkovich space associated to that, or?
Well, I mean, I don't, you know, I think this is exactly what tropical intersection theory is giving us, right? It just, you know, I claim that tropical intersection theory, while usually not stated in this way, should be able to be formulated in terms of algebra over the tropical hyperfield. And by doing that, we should be able to see this analogy more closely with things like Descartes' rule. But it's not, this is kind of still in progress. And yeah, I mean, there's actually further analogies. You mentioned Berkovich spaces. I mean, there's a kind of signed analog of that where you look at a space of all orderings on a field, and you know, this has been studied in the real algebraic geometry literature, and it's quite analogous to Berkovich spaces. So I mean, I think these things are very interesting. But so let me go on to talking about matroids. And I have a few more slides in Keynote, and then I'll switch to Beamer. So most people say that Whitney was the pioneer of matroid theory. I mean, there's some interesting historical notes on this. There was some work by a mathematician named Borufka before Whitney, and simultaneous work by a Japanese mathematician, Nakasawa. But I'm not a historian, so I won't try to get all that right. But here's the definition as Whitney would have given it. Actually, I think Whitney had the symmetric form of basis exchange in his original work, and this turns out to be equivalent. But matroid is a finite set E together with a non-empty collection script B of subsets called the bases, so that for any two bases B and B prime, and an element little b of one but not the other, there's a complementary thing, little b prime, which the property that when you add little b prime and throw out little b, you again get a basis. And so this is known as the basis exchange axiom, and it's one of many different ways to axiomatize the theory of matroids. By a familiar argument from linear algebra, this exchange property shows by induction that any two bases have the same cardinality, and that common cardinality is called the rank of the matroid. All right, I'll again skip the amusing quotes. You have my slides if you want to read these things later on. But ROTA has many colorful quotes about matroid theory. You know, matroids are meant to capture some things from geometry. So this is in a sense a picture of a matroid. Maybe I won't get into the details of how you're supposed to interpret this. Most of you know this already. But it has to do with configurations of points, lines, planes, etc. But for this talk, I want to emphasize the connection to Grassmannians. So suppose K is a field and W is a two-dimensional subspace of K to the 4, right? So as we know, this gives rise to a point on a certain Grassmannian, and that Grassmannian has certain Pluker coordinates. So you can say this in terms of exterior algebra in a very natural way, but let's just be as concrete as possible. Represent W as the row space of some 2x4 matrix A. And now look at all the 2x2 submatrices and let Aij be the determinant of the submatrix corresponding to columns I and J. And those quantities, Aij, are not algebraically independent, right? They satisfy this Pluker relation that I've written down, which I'm sure is familiar to almost everyone here. So the point is that these Pluker relations are intimately connected to matroid theory. And let me try to explain that. So first of all, right, the point of the Pluker coordinates is that they allow you to embed the Grassmannian in projective space, because this vector, as a point of projective space, actually doesn't depend on any of the choices we made. It's an invariant of the subspace W. And a point of P5, which satisfies that Pluker relation I wrote down, comes from a unique subspace W. And that's the theory of Grassmannians in a nutshell, at least in this particular case, where there's only one Pluker equation. In general, there's many. So that's what I wrote here. We have the Grassmannian GRN, and it's defined by some equations called the Pluker relations. All right, and they look like this. Let's not worry about getting all the signs right in this talk. But you know, they have some flavor where the only tricky thing is to kind of get the alternating signs right. And for that, you maybe need some ordering convention or some, later I'll give a different way to nail down the signs. But again, I'm sure this is familiar. So what I want to emphasize here is that if you have a hyperfield F, it makes sense to look at the solutions to the Pluker equations over F, because you can simply write down those Pluker equations formally, replace the plus signs by hypersums, and now instead of setting it equal to 0, ask for 0 to belong to the hypersum. So in a totally formal way, you can look at all projective tuples with coefficients in a certain hyperfield for which 0 belongs to this hypersum. And the theorem, which I mean, I was the first one, I think, to write it down in this way, but it's clearly a known idea before. When F is the Krasner hyperfield, there's a completely canonical one-to-one correspondence between solutions to the Pluker equations over K and matroids of rank R on the set 1 through N. So this gives a completely precise meaning to the analogy between matroids of rank R on an n-element set and the Grassmannian GRN. People often talk about that as an analogy, but it's in fact two examples of a more general phenomenon. So there is some kind of more universal type of Grassmannian that lives in some funny algebraic world, whose k points for k, the Krasner hyperfield, give you matroids, and whose f points for f a field give you the usual Grassmannian over f. So Oliver and I wrote a very long paper that I'm not going to describe in more detail now, making this precise, defining a certain moduli space in the world of ordered blueprints, whatever those are, and proving that, you know, there's some Grassmannian type thing representing a moduli functor, et cetera, and to just set up the necessary algebraic geometry requires some work, making certain things from Hartshorne, for example, like work over more general algebraic structures. And I don't want to get into that because it gets technical and will probably put you all to sleep, but it's interesting. I hope you agree, if you're willing to do the grunt work. And what's I want to emphasize now, though, is that there's other hyperfields for which this is interesting too. So if you plug in the hyperfield of signs and you just do the same thing I just described, now you just get exactly oriented matroids, which many of you know what that is. And if F is the tropical hyperfield and you do what I just described, you get valuated matroids or tropical linear spaces. And so I think this is really the right way to unify these concepts and to look at certain aspects of matroid theory as being points on a certain Grassmannian.
So
and with that, I'll take a short break. Yeah, question.
Excuse me, so does this allow you to speak, for instance, of algebraic curves of matroids or surfaces of matroids and kinds of things like this and ask interesting questions about them?
It definitely lets you ask interesting questions. We haven't yet solved interesting questions using that, but yeah, in principle, in our paper, we have a notion of a family of matroids over an arbitrary base, which can be any ordered blue scheme with some property. And so, I mean, this is a very general thing. But I mean, we don't really have a well-developed notion of, say, flatness that would give you some constancy of numerical invariance or something like that. So, I mean,
and have you already met this object in a different language elsewhere in the literature? Such families of matroids?
Not sure. I mean, it's related to other things in the literature, but you know, it's hard to make precise comparisons sometimes. But anyway, I think this notion of family of matroids over an arbitrary base, certainly one of the things we had to do in our paper. Okay. So we had to define line bundles on ordered blue schemes and things like this. But yeah, it works.
Thank you very much.
Sure. So what I'm going to do is share my other slides now. And we'll sort of continue, but now I'm going to pick up the pace a little bit and be a little bit more I guess assume a little bit more background on matroids, but I mean, I still think it'll be self-contained even if you're not an expert. It's just I want to go a little faster to cover some more material. Can you all see the Beamer slides? Okay. So, so I'm changing gears a little bit, but I mean, as you'll see, the algebraic foundations are really kind of very similar to what I've been talking about now. It's just the tropical connection will be slightly less clear here. So, because somehow looking at representability of matroids over the tropical numbers it's kind of interesting, but not as interesting as over some other hyperfields, I think. So, So representability, of course, say over a field, finite fields and things like this is one of the main things people in matroid theory have studied. There's a notion of representability over partial fields, which I'll define soon, which matroid theorists have learned is quite important and interesting. And one of the things that, I was asked about early on by experts was whether one can incorporate this so-called universal partial field into the world that I was trying to advocate for with hyperfields and all that. And I thought it was a really good question, and I didn't know the answer. So there's something called the universal partial field, which we'll understand more about in a moment, which sort of governs all the representations of a given matroid over all partial fields, which include all fields. But there's some unsatisfactory aspects to the theory of the universal partial field, at least to me. And maybe one of the main ones is that if you pick a random matroid, whatever that means, then with probability essentially 100%, it will not be representable over any partial field. So, I mean, in that case, there sort of is no universal partial field and the theory is completely empty. So asymptotically, the existing theory didn't actually say anything about most matroids. That's one problem. Another problem is that representing over things that are not partial fields, like the sign hyperfield, which talks about orientability of matroids, is also a well-known interesting thing, and that wasn't part of the previous theory. So Oliver and I set out to kind of generalize this stuff in a way that would work for all matroids and would include things like orientability. And so the way we do this is using something we call the foundation of a matroid. It's a kind of generalization of the universal partial field, and it exists for every matroid and gives non-trivial information about, for example, reorientation classes of oriented matroids. So that's the motivation. And to do it, we'll need to do a couple things. One is to go beyond hyperfields and beyond partial fields as well, and give a simultaneous generalization of those, which I call pastures. And now we'll also need to kind of define representing matroids without explicitly mentioning matrices, because often matroid theorists define representations in terms of being able to write down matrices, but this is less well behaved in this more general algebraic context, so you need a more abstract point of view, I guess. All right, so this is what we're going to do. So we'll have pastures, we'll have a notion of representations over arbitrary pastures, and then we'll have this pasture called the foundation, F sub m, with some universal property that hum from Fm into any pasture P gives you the so-called rescaling classes of representations of M over P. And if I have time, I'll tell you exactly what that means. But anyway, it's a universal property that even in the case of the universal partial field was lacking. There wasn't a kind of canonical identification of homomorphisms with equivalence classes of representations. There was a weaker statement in the literature. So our functorial point of view makes everything a bit sharper. Okay, so I want to tell you what a pasture is.
Matt?
Yeah.
Should we think of FM as the pasture of definition of the matroid?
Yeah, it's very much like that. I mean, it's not precisely that for some technical reasons that I can mention at the end, but this is actually how we discovered it. Was it's essentially you take the residue field, or it's not a field anymore, but whatever, residue pasture of a certain point on the moduli space of matroids. And then you have to do a certain operation to it, which is a functorial thing. But anyway, then you get the foundation. Yep. Any other questions? Okay, so yeah, so I guess I want to take a different point of view now. So instead of looking at hyperfields which have a multi-valued addition law, let's think about it in a slightly different way. We're just going to give up on the notion of a binary operation as the key thing. So a field, right, you can think of as an abelian group G together with some element 0. And then you have a binary operation on G union 0 that satisfies some natural axioms, associativity, distributivity, blah, blah, blah. So for Pastures, it's similar. We have a multiplicative abelian group P star and an absorbing element 0 and some kind of additive structure, but it's not going to come from a binary operation in general. So what does that mean? So let me give you 2 examples, and I think it'll be very clear what I mean. First is one we've already seen, the Krasner hyperfield, but I want to describe it as a pasture rather than as a hyperfield. And so here's what that means. We have the multiplicative monoid 0, 1. 0 is an absorbing element, 1's a multiplicative identity. And then we have some collection of additive relations of the form A plus B equals C. And the ones in the Krasner hyperfield are these, that 0 plus x is x for any x, 1 plus 1 is 1, and 1 plus 1 is also 0. So before we were calling that a multi-valued operation and setting 1 plus 1 equal to the set 0 and 1, but it turns out it's actually better in many, many ways to instead simply say we have a list of additive relations that hold here, and 1 plus 1 equals 1 and 1 plus 1 equals 0 are both valid relations. Okay? A slightly different point of view. And now I can tell you an example of a partial field. It's called the regular partial field because it's related to regular matroids. And the multiplicative monoid is 0, 1, and minus 1. And multiplication is the obvious thing. And now what are the additive relations? You always have 0 plus x equals x. That's going to be an axiom. And here we have the additional relation that 1 plus minus 1 is equal to 0. But there's no relation of the form 1 plus 1 is equal to anything. Right? So 1 plus 1 equals x. There are no x's for which that relation holds. So again, it's not coming from a binary operation, because if it were, then you'd have to say what x is. So you can think of this as just 1 plus 1 is undefined rather than being multi-valued. And that's fine, but again, it's a little hard to work with undefined binary operations. It's an awkward notion. For example, what does it mean to be associative if something's partially undefined? So it turns out it's just much better to stop losing sleep over things like associativity. And that's what Pastures do, is they give you more sleep. So if this F1 plus or minus, which the name comes from some conventions I might not get to, but it's of course encoding the restriction of addition and multiplication in the integers to the subset 0, 1, and minus 1. And if it were just 0 and 1, I would call this F1. And this is related to F1 geometry. But to do matroid theory and the kind of things I want to do, it's crucial to have this minus 1, which might be the same as plus 1. But I mean, you do need a notion of sign to talk about, for example, Pluker relations. Okay, so the unification is this, that a pasture P should have an involution x goes to minus x, which in some cases like Krasner or tropical would be trivial. And instead of writing things as x plus y equals z, we'll rewrite all our relations as like x plus y plus something else is equal to 0. Just move z to the other side using the involution. So in that way, we're always looking at 3-term relations, which we're saying are either 0 or not. And that just makes it easier to axiomatize what we want, okay? And once we do that, addition is supposed to be commutative here. So if a plus b plus c is 0, then b plus a plus c should also be 0, etc. So we can just look at triples ABC, which are symmetric under permutations. And the set of all such triples will be called the null set of the pasture. So formally, here's what I'm saying. A pasture is a multiplicative monoid with 0, such that p minus 0 is an abelian group. You have some involution, x goes to minus x, which fixes 0. And then you have a subset of p cubed with the following axioms. It should be symmetric, as I was just trying to explain. It should be weakly distributive, which means you multiply by anything in p star if you're still in the null set, right? So it's sort of if a plus b plus c is 0, then you should be able to multiply the left-hand side by something in p and it's still 0. And then you have this unique weak inverses property that 0xy is null if and only if y equals minus x, which is to say that x plus y should be 0 if and only if x and y are inverses. And that's it. Those are all the axioms. So it's actually a very minimal set of axioms. And there's no associativity axiom at all here. So if you were to try to define a multivalued operation x plus y in this way as the set of z's for which x plus y minus z is in the null set, then P would be a field if and only if this is an associative binary operation. But we're giving up on those things now. And if it contains at least one element, if that hypersum is always non-empty and it's associative in a suitable sense, that's actually what it means to be a hyperfield. And if this hypersum of sorts, it contains at most one element for all x and y and satisfies some version of associativity, it's called a partial field. But we're just going to drop all those extra conditions and we get pastures. So in a way, it's just simpler because we have fewer axioms. So examples, we've already seen examples of hyperfields, so I'll be real quick here, but a general construction is you could take a field K and a subgroup G of K star, and then there's a quotient monoid K mod G, and there's a natural hyperfield or pasture structure on it. In this way, you get, for example, the Krasner hyperfield as R mod R star, and the hyperfield of signs as R mod the positive reals. But be careful, not every hyperfield arises in this way. In fact, I have a conjecture with one of my students that something like Peter Nelson's theorem should hold that asymptotically all finite hyperfields are not actually quotients of fields. This is in fact related to the Weil conjectures in an interesting way, but I won't get into that now. And examples of partial fields would be you take a commutative ring R and a subgroup G of R star, which contains -1. And now once you throw in 0, you naturally get a partial field. The additive relations are exactly those expressions that only involve the subgroup G and 0 and which hold in the ambient ring. And actually every partial field does arise from this construction. So if you want, you could take this as the definition of a partial field. And then P of R, if R is a ring, is the special case where you take G to be the whole unit group at R star. And in this way, you get the regular partial field I mentioned. It's just P of Z. You get the so-called dyadic partial field D, which is associated to the localization of Z at the prime 2. There's the sixth root of unity partial field H. The near regular partial field U, which might look funny, but it's related to the matroid U24, uniform matroid of rank 2 on 4 elements, which is related to that Grassmannian example we talked about earlier. And the theory of cross ratios in geometry interacts very nicely with this near regular partial field U. So matroid theorists know about all these things already, but we're just axiomatizing them in a different way. all right, I want to get to some actual theorems. So let me just say there's an obvious notion of homomorphism of pastures, which is exactly what you think. Null set maps to the null set, and 0 and 1 are preserved. And I think this automatically implies that negation is preserved as well. And the cool thing is that now we can see that this regular partial field that's interesting in matroid theory is actually the initial object in the category of pastures, and the final object is the Krasner hyperfield. So that's nice because they just show up naturally now. And pastures, unlike fields, unlike partial fields, unlike hyperfields, have arbitrary limits and co-limits. And this is useful for various constructions like universal partial fields that we'll get to in just a moment. So yeah, this is a key advantage here that gets rid of some of the pathological properties of hyperfields. So if you have a matroid, what is a representation over a pasture P? Okay, I see I only have a few minutes left, so let me be slightly impressionistic here. I just want to be able to state the main theorem about existence of a universal partial field called the foundation. So a representation of a matroid, as I said, we don't want to define it in terms of matrices. Instead, we'll define it as something that looks like the determinant function on maximal minors of matrices. Namely, and let's say the matrix has rank R, the fictitious matrix that we're imagining modeling this on has rank R, so that means the determinant is non-zero if and only if you have a basis of your matroid. If you permute things, it just changes by the sign of the permutation. Right? That's what permutations do to determinants. And then this function should satisfy the three-term Plucker relations, which we've already said make sense in any pasture. And for technical reasons, I'm only looking at the three-term Plucker relations, not all of them. And that's actually a long discussion that I don't have time for, but you can ask later if you want. So the point is, there's a natural notion of representations that doesn't really refer to matrices at all. And we'll say a matroid is representable over pasture P if there's at least one P representation. And there's a natural notion of isomorphisms of representations, which is just rescaling the determinant function by some scalar. And yeah, okay, some technical remark that I'll skip. And there's a finer equivalence relation that matroid theorists know is useful called rescaling equivalence, which there's no reason to dwell on this since I'm almost out of time, but you allow some additional rescaling on each, adapted to each element of your ground set. So it'd be like rescaling the columns of a matrix by some scalar. And it doesn't change which matroid you're representing when you do that. So we have two notions, I for isomorphism and R for rescaling classes of these kind of moduli spaces of representations. And for over a field, these are just familiar things. These correspond to matrix representations. And every matroid is uniquely representable over the Krasner hyperfield. So in particular, every matroid is representable over some pasture, which will guarantee that our universal thingy is non-empty. And it's compatible in a certain precise sense with the notion of universal partial fields, but let me skip that since I don't have time to get into that anyway. And yeah, I'll skip that remark too. So here's a theorem. The functor that takes a pasture, so fix a matroid M, the functor that takes a pasture to the set of isomorphism classes of P representations is representable by a pasture called the universal pasture. So there's a natural isomorphism of functors from this kind of realization space to hum PM into blah. And there's something similar for rescaling classes which is representable by a certain subpasture of the universal pasture that we call the foundation. Foundation's a little bit simpler to work with and is better adapted to matroid theory questions. And so it's the central object that Oliver and I have focused on. And it also represents a certain functor. And so very, very quickly, I know I'm out of time, but the universal pasture, just some impressionistic properties. The universal pastures or foundations, let me just focus on foundations. The foundation of M and its dual matroid are canonically isomorphic. There's a canonical homomorphism from a minor of a matroid, from the foundation of a minor to the foundation of the matroid itself. And if the foundation is a partial field, it is the universal partial field that was defined before. A matroid is representable over two given pastures if and only if it's representable over their product pasture. And if you have two matroids, the foundation of their direct sum is the tensor product of the foundations. So I'm just pointing out all these things cannot really be formulated in the usual language that people use, because partial fields don't have these same operations of, say, tensor products, nor do hyperfields, nor do fields. So you really need some version of our language to do this. And just to illustrate really quickly the utility, if you take the product of F2 and F3, these finite fields considered as pastures, it's isomorphic to the regular partial field. That's just a dumb exercise you can do. So you immediately get this theorem of Tutt that's considered in the combinatorics literature a deep theorem, that a matroid is representable over every field if and only if it's regular. Okay, maybe I don't have time to say all the words that justify this, but it's very easy from this point of view. And it's just a categorical statement now. And you can get similar things like the theorem that a matroid is representable over F3 and F4 if and only if it's hexagonal, which means representable over the sixth root of unity partial field. And so you can just unify a lot of stuff in matroid theory in this way. But pastures actually give you even more. For example, you can now prove something about binary and orientable by looking at the product of F2 and the hyperfield of signs, which is also the regular partial field. And this gives us a proof of a theorem of Blanda and Las Vernias. And one can go even further, but I think I'm out of time, so I will leave it there and see if there's any questions.
So let's thank Matt for the nice talk, however you prefer.